Previously, we have discussed several techniques for comparing population means from two populations. For independent samples, there are two sample z-test and two sample t-tests. For paired or matched samples, there are paired t-tests. These tests are useful for two populations, but fail when the number of populations is more than two. In this presentation, we will discuss a powerful statistical technique that works for population mean comparison when the number of populations is 2 and above. It's called the analysis of variance, also known as ANOVA. We will illustrate this technique using the following example. Consider the scenario that you are the manager at the customer satisfaction department for a large commercial airline. You are curious to find out whether passengers are equally satisfied with the service across different travel classes, including first, business, and economy. To carry out this study, you would probably carry out a survey to see how satisfied customers are with their flight experiences. A typical survey looks something like this. You're going to ask the customers, could you please rate your satisfaction with this flight on a scale of 1 to 7? With 1 being terrible and 7 being excellent. After a typical flight, you were able to ask 9 first-class passengers, 14 business passengers, and 11 economy passengers about their flight experience. Their satisfaction scores were presented in a table on the right. You were also able to compute the sample means and also sample standard deviations for each of these 3 travel classes. We would like to carry out a hypothesis test to see whether average satisfaction scores are the same across 3 travel classes. Typically, the null statement says there is no effect, meaning the population means are the same. The alternative statement says that there is some kind of effect, meaning the population means are not the same and the passengers from one travel class provide significantly higher satisfaction scores than the others. It's worth noting that we do not need all 3 population means to be different from each other. We just need one population mean to be different from the rest for the alternative hypothesis to hold. There is a total of 3 populations here. The statistical techniques we learned before for 2 population mean comparison will not work here. Instead, we will use one-way analysis of variance, also known as ANOVA here. One way here refers there is only one independent variable of interest under consideration, and that is travel class. Travel class is also the factor here. There are 3 different levels for this factor: first, business, and economy. They are also the treatments. ANOVA is mostly used to evaluate the difference among means of 2 or more groups. Some examples include to compare accident rates for morning, afternoon, and night shifts. Or maybe we can compare the expected mileage from 5 different brands of tires. ANOVA works especially well for multiple mean comparison, based on several assumptions we make. We would have to assume the populations we are comparing with all follow normal distributions with the same variance. They do not need to have the same population mean because we use a ANOVA test to test whether they have the same mean or not. For each population, the samples are all randomly and independently drawn to ensure the samples are representative of the population they are from. Let's take a closer look for the hypothesis of ANOVA. The null is all population means are the same. This suggests that there is no factor effect or no variation in means among different treatments. The alternative is not all means are equal, suggesting that there is a factor effect. We do not need to have all means to be different from each other. For our passenger satisfaction example, we would have 3 bell curves to represent satisfaction scores from 3 different travel classes. From the constant variance assumption for ANOVA, the 3 bell curves should all have the same spread. If the null is true, meaning the population means are the same, then the 3 bell curves should all have the same center. If the null is not true or the alternative is true, there will be 2 different outcomes. Either two population means are equal but different from the third one, or all three population means are different from each other. The term of analysis of variance implies that we would have to focus on the variance. We divide all the variation present in the dependent variable, that is the satisfaction scores of passengers, into two parts: variation or maybe variability due to factor, and variation due to random error. The total variation is generally denoted using SST, meaning total sum of squares. T is for total. Variation due to factor is denoted as SSTR, meaning sum of squares due to different treatments. TR stands for treatment here. Variation due to random error is represented using SSE, sum of squares due to random error. E stands for error here. The relationship between three different sources of variation is that SST is the sum of SSTR and SSE. I will describe each of these three sources of variation in more details in later slides. SST is the total variation, that is aggregated variation of individual values across different factor levels or treatments. There are travel classes in our example. SSTR is also known as the between treatments variation. It measures the amount of variation among different treatment means. SSE is also known as the within treatments variation. It measures the amount of variation that present within the same treatment. I will explain how to calculate each of these three sum of squares. Before we do that, we would need to introduce some notations first. I will use K to represent the number of treatments. So for our satisfaction example, K is 3. Nj represents the total number of observations in the jth treatment. There is a total of 3 treatments here, so J runs from 1 to 3. N1 is 9, N2 is 14, and N3 is 11. N with subscript capitalized T is the total sample size in this survey. That is the sum of 9, 14, and 11, so 34. Typically, we use X with 2 subscripts to represent the ith observation from the jth treatment. For example, X21 is the second observation in the first treatment, so that is the first class. Therefore, X21 is 5. X bar 1 is the sample mean of all first-class passenger satisfaction score. That is 3.78. X bar 2 is 3.86, and X bar 3 is 3.36. I will use X with double bars to represent the grand mean. That is the mean of all satisfaction scores across all 3 classes. This number is found to be 3.68. This is not the average of X bar 1, X bar 2, and X bar 3, because different travel classes have different numbers of passengers. We would have to add up all individual scores and then divide by 34 to get this grand mean. To find an SST, we compare each individual observation X with the grand mean of 3.68. To prevent any cancellation between positive differences and negative differences, we square the differences before summing them up. That's why this is called the total sum of squares. This is calculated to be 127.44. Due to the sheer amount of data, we are not expected to compute this sum of squares by hand anymore. But it's good to be able to understand how each of these sum of squares is calculated. For SSTR, which is between treatments variation, it measures the amount of variation in satisfaction scores entirely due to different treatments passengers received. This source of variation is completely because different passengers travel on different travel classes. SSTR is calculated by comparing each treatment mean with the grand mean. Again, we square the differences between treatment mean with the grand mean, and then scale each treatment according to the number of observations in that treatment. We add up all the squared differences. SSTR is calculated to be 1.63. The last source of variation is SSE, that is the amount of variation due to random error. Despite the fact that some passengers travel on the same class, they may still give different satisfaction scores. SSE counts for this part of variation. That's why it's called within treatments variation. The variation with each treatment is measured by the spread term. That's the variance or squared standard deviation. Using the sample information from the samples, mostly the sample standard deviation and sample sizes, we calculate the SSE to be 125.815. Again, you are not expected to compute SST, SSE, or SSTR in the exam condition. I just want to show you how these three different sources of variation can be calculated. Adding up the SSTR with SSE, that is 1.626 plus 125.815, we are able to get 127.441. That's exactly SST. Out of these three sum of squares, actually we don't need to compute for each of them. We just need two of those three, then we can figure out the remaining one using this equality relationship. As we have seen earlier in the slides, for ANOVA analysis, we would need to set up a hypothesis test and compute a test statistic to be able to claim whether we have enough evidence to reject the null or fail to reject the null. We will set up an ANOVA table to help us in this analysis. The first column of this table is different sources of variation, which we have discussed before. They are between treatments variation, within treatments variation, and the total variation. The second column is the sum of squares. Between treatments variation is also called SSTR. TR stands for treatment. SSTR is found to be 1.626. SSE is the within treatments variation. That is calculated to be 125.815. And SST, the total variation, is 127.441. The third column is degrees of freedom. The degrees of freedom for between treatments is always k-1, where k is the number of treatments. For our passenger satisfaction example, that is 3, so degrees of freedom for between treatments is 2. The degrees of freedom for the last row, that is for total, is n with a subscript capitalized t minus 1, where nt is the total sample size from all treatments. That is 34 minus 1, so 33. To find the degrees of freedom for within treatments, we can use the difference between the degrees of freedom for between treatments and the degrees of freedom for total. That is 33 minus 2, so 31. This kind of equality relationship for degrees of freedom is the same as the equality relationship for sum of squares, because SST is SSTR plus SSE. The next column is called the mean square, which can be calculated using sum of squares divided by its corresponding degrees of freedom. For example, for between treatments, MSTR is SSTR divided by its degrees of freedom. So that is 1.626 over 2, that is 0.813. For within treatments, the mean square is MSE, that is SSE over its degree of freedom. MSE is calculated to be 4.059. It's not necessary to compute a mean square for total, so I will leave this one out. The last column of this ANOVA table is for F ratio. That is also the test statistic for this test. F ratio can be calculated using MSTR over MSE. We find this to be 0.20. Let's summarize the ANOVA test in this slide. The null is all means are equal, and the alternative is not all means are equal. The test statistic is an F ratio, which can be computed using the ratio between MSTR and MSE. F distribution is another distribution. It looks a little bit like a chi-square distribution, but with two different sets of degrees of freedom. The first degrees of freedom is called the numerator degrees of freedom. That is the degrees of freedom for the numerator of the ratio. so that is due to the treatments. The second degrees of freedom is also called the denominator degrees of freedom. This is the degrees of freedom for the denominator of the F ratio. That is due to the random error. This is an F distribution table. F distributions share many similar properties as chi-square distributions. It's not a symmetrical curve like a Z distribution or T distribution. All F statistics are non-negative values. The smallest F statistic is 0. This table is ordered by two different sets of degrees of freedom, the numerator degrees of freedom and the denominator degrees of freedom. And just like the chi-square table, only the upper-tailed probabilities are given. When we work on F-tests, we usually only deal with upper-tailed probabilities. The p-values are the upper-tailed probabilities associated with the F statistic. Let's use this F table to find the p-value for our test. The degrees of freedom are 2 and 31 respectively. The test statistic is 0.20. The p-value is the upper-tailed probability for 0.20. The table does not have degrees of freedom being 2 and 31, so I'm going to use 2 and 30 instead. Using the table, we know that for 2.49, the upper-tailed probability is 0.10. Our test statistic is 0.20, which is much smaller than 2.49, meaning 0.20 is on the left-hand side of 2.49. So its corresponding upper-tailed probability should include the upper-tailed probability for 2.49. That means our p-value is much bigger than 0.10. Therefore, we would reject the null and conclude the population mean satisfaction ratings are equal across 3 different travel classes. We could also solve this problem using the critical value approach. For degrees of freedom 2 and 31, the critical value would be very close to 3.32. Because our test statistic is much smaller than the critical value, we do not reject the null at 5% significance level and arrive to the same conclusion as that using the p-value approach. This concludes the passenger satisfaction example using the ANOVA test.